We should be good to go. How's everybody doing? Did everyone else wake up and it was like pouring down hurricane rain and stuff?
Yeah.
That's always fun to wake up to. What's up?
Is the lab today for everyone?
No, that's yeah. So sorry about the whole confusion this week with everything. I was not planning to get stuck in the Midwest for 2 extra days. Surprise, as fun as that sounds. So yeah, what I'm gonna do, the first lecture on Monday or Tuesday, we're just gonna be able to make that up. So I'm not gonna record anything. There's gonna be nothing, that you have to watch regarding that. For the lab, I'm still trying to play so much catch up. I don't think I'm gonna have time to even have an in-person lab section this week. Next week, I think what I'll still do is have some in-person opportunities for the lab this week. Because it's a permeability lab, it's kind of like cool to see it firsthand if you want to, but it's 100% optional. So did everyone see the videos posted from like 2020 and kind of like on whatever it is on Canvas? Did you guys see those? Okay, so if not, I'll make an announcement, but the virtual lab from when we were all virtual and stuff, I made videos for all the labs and I posted those on Canvas. And so there's the recorded lecture section of the lab and then just like a dumb like blog style, like, video of the lab experiment being handled. So what I want everyone to do is watch that and then use the data from that lab for your lab reports. So you'll see the lab report is due next week and it's all due on the same day. I'll probably push it back now because not many people have been able to watch it. But just with missing Monday and Tuesday and half of Wednesday, I didn't have time to schedule in-person stuff. Yeah.
So there is no lab for Thursday today?
Right, no lab for today. Yeah, there's no lab today either. So I'll have more input next week about opportunities if you still want to come to the lab and work with this lab firsthand, but everyone should watch the video and it tracks who watches it or not. So I'll make an announcement after that. It's required to watch the lab video. So apologies for all that stuff. You can write an email to Spirit Airlines if it's like I have. Yeah, never doing that again.
I think you still have 5 in a bucket.
Oh yeah, amazing. No, they smooched us, man. They upgraded us to like the big seats on the way there. Like I mean the normal size seats, I should say, but the big seats for Spirit. And then on the way back, they canceled 3 flights back. So they were, yeah, that wasn't fun. Yeah, so for Lab 7, it's going to be a video only. So they're going to be posted on Canvas. You can watch those, and then you're still going to work with your lab group. In the video, there's data that like pops up on the screen. So you're going to have to watch the video and record the data just like you'd be doing the lab in person. And there is going to be in-person opportunities to watch this lab because it is, important. That's going to be next week and it's optional. So I don't expect you guys to come. Exam 2 just kind of got set back with grading. So I'm still working on those, but I will hopefully have those posted by the weekend. And there is no quiz this week. So just wanted to, we're kind of doing like a hard reset week with all the hiccups and travel and stuff. But what we are covering is really important today. So we're going to start covering in situ stress. That's like the whole last half of our class or last third of our class. And it's really important moving forward. You will see this material on the FE. If you're going into geotech, you will use this in every single aspect of design. And we'll definitely see it on the PE if you decide to take the geotech PE. So, just keep that in mind. We're only covering one subject for this last exam, but it's just a super critical one. Any questions on where we're at so far? Semester, I know how many weeks do we have left? 4? Yeah, so we're almost done. Just gotta chug Red Bull and coffee and we'll be done soon. Happy opening day too. Any baseball fans? Yeah. You want to? Oh, the jumbo shrimp. I still haven't been to a jumbo shrimp game. I really want to go. Yeah, so now I'm going to switch my office hours. I'll have office hours available in December when baseball season is over, just to account for all that. No. All right. In situ stress. Has everyone heard of the term in situ before? think I've used it sometimes, but I always forget that it's not like a normal word. In situ just means like in place. So like the current conditions underground at whatever depth we care about. So we're going to talk about the stress of the soil at a depth that we care about. So if we are designing a tunnel 100 feet down, then the in situ stress is going to be 100 feet down. That, you know, if we are obtaining a clay sample from like 300 feet down, then the in situ stress would be of that clay sample 300 feet down. So what we're going to be covering is in chapter 10.14 and 6.9. If you do, for the half of you who actually look at this textbook, just know that we are only covering the saturated soil. This textbook goes a little bit further into the theory of like unsaturated soil mechanics. But you'll see in some of these chapters, if you actually read through them, they'll cover unsaturated. We're not covering unsaturated soil, only looking at saturated in this case. All right, so what we were talking about before the exam last week or whenever that was, we know that water, we can measure the flow of water through soil, and water will always seek to find equilibrium. So it always seeks to find this hydrostatic condition. And we talked about the seepage, like flow rate of soil using this equation. This is the flow net equation, right? And this allows us to find the Q value. The Q value is the flow rate of water. Now you can probably imagine if we increase this flow rate too much, we would have a flow rate of water that could potentially dislodge the soil particles, right? Like it's a garden, like think of a garden hose. If you spray a garden hose on water or on like the beach and the sand is super dense or the water is the flow is really low, then it's not going to do anything. But if you increase the flow rate, then you could potentially have the migration of soil particles. So this is really important in geotechnical engineering. In terms of a few things, and we've mentioned these before, but like quicksand, even though it's not really called the movie version of quicksand is different than what is actually happening with quicksand. But liquefaction in earthquakes, this is all due to like the movement of water and actually the dislodging of particles. There's another issue called heave, where we actually have the water stresses moving a chunk of soil along, like the weight of that is a little bit heavier, and the weight of like a chunk of soil like is matched by the water pressure, and we'll cover that. But the big thing that this affects is the intergranular stress. And so the intergranular stress, this is when we actually zoom in on like a chunk of soil and we think about the interaction of all these soil particles with each other. And you can probably imagine that it's, these little tiny chunks, like almost like aggregate, and they are all interacting and contacting with each other. And this greatly affects the strength of the soil. So what we want to eventually do is construct something on our soil, geotechs, we want to transfer the structural loading of a bridge, a skyscraper, a road, whatever. And we want to transfer those loads into the soil and through the soil. So we need to estimate the soil strength and the ability for that soil to hold whatever we want to load on top of it. So like the flow rate stuff, we've already seen like stuff like that before. And that's the flow rate shown there. So we have a seepage force, and the seepage force is technically this drag force that develops at the interface between flowing water and the soil particles. So we could actually like zoom in and think on the granular level that we have a water molecule hitting a soil particle, and there's something holding that soil particle intact. So we know that seepage force, what we usually care about is stress. So the question is, what is causing this soil resistance? And I already put all these marks here, but so what is causing the soil resistance is that intergranular stress. And what is or how we determine that intergranular stress is actually through the in situ stress. So if you think about it, like trying to pick something up, like if you had a stack of weights or just one weight, right? Or let's like say like a book or something instead. If you have just like one single book, it's kind of easy to pick that up, right? Like you just have to match the weight of that book. But if we had a stack of books going all the way up, then that would be much heavier to pick up. So we see the same thing with soil with depth, right? Like the deeper the soil particle is, the more soil there is on top of it, the higher in situ stress it is, and then the more difficult it is to transport that soil particle at a certain depth. So let's look at like an imaginary cross section. We just take, Jacksonville, and we cut a big slice of pie down the center. We see a sand layer, clay layer, and our little house at the surface. Let's zoom in at like this little make-believe circle here. So if we were to, even though we picture soil on like a macro scale like this, if we were to zoom in and look at it on a micro scale, what we would see is a bunch of interlocking particles. And these little interlocking particles, this is just some like arbitrary volume. So let's just say this circle is like a unit volume or something. These little interlocking particles all have points of contact, right? So on the skeletal level, it's very difficult to analyze this stress. It's not like a method of joints or in like a truss where you can easily measure the cosine between all of these and like do the math to determine how force or weight is transmitted from one end to the other. So most of the time we analyze the soil mass as a body. And this is the super important reason why we care about densities. Because let's think about what this circle is. This circle is just a volume. Let's say it's like a sphere that's cut out of the circle. So it's actually a 3D sense here. Let's just say this is a sphere, and let's just call that sphere having a volume of like 1. So like 1 cubic foot or something like that. So how we actually determine this as a body is we look at all the things that have mass within that sphere, and knowing that the density is mass divided by volume, we use that density as a determination of how forces are transmitted through the z direction or through the depth direction. So we analyze this soil as a mass or a body. And we know that if we were to look right underneath it, there would be a force exerted from the amount of soil above it. And then likewise, above it, there's also a force exerted from the soil above that. So instead of force, since we're engineers and we like to normalize force per a cross-sectional area, we look at this in terms of stress. And what this is called the total stress. So it's just think of it as like a dog pile. Like at this point of soil, there is a certain weight of object or material above it, and that is also exerting a total stress or weight of material below it. So the combination of the weight of material, if we have a volume, and we look at this point, then what we could actually do is just say like, okay, there's a bunch of equal circles above it that is causing the same exact amount of weight. So what we actually use is the density, the bulk unit weight shown here. And again, in this circle, we only have potentially 2 things that have weight. We have the weight of the solid, right? We have the weight of the solid that has weight, and then we also have the weight of water, if there is water. So thinking back to the void or the phase diagram, air doesn't have weight. So the only 3 things there's 3 things that compose of soil, like we assume, and the weight of this solid, is 1, and then the weight of water is the other. So that's the density. So what we assume here for this is we assume that this sand is homogeneous, which means the density here is equal to the density here, which is equal to the density here, which is equal to the density here, here, here. So the whole soil layer has the same consistent amount of density. And what we're also assuming here is that is hydrostatic. Before hydro meaning water, static meaning not moving. So there's no flow, there's no seepage through the soil profile. So if we were to look at point A and estimate the stress that is felt at a soil particle or object or a person or a bug or whatever at point A, the weight up from the soil above it can be defined as the total stress. And we show this as a sigma. So anytime we're talking about a total stress or a vertical stress, we show this as a sigma. And this is equal to the density of our soil times the height of the soil above it. And this density, this gamma, is right here. It's everything that could potentially have mass. So if there's water in it, then we include that. If it's just soil and it's all dry, then we take out the water term. And think about what the units are in this. This is equal to pounds per cubic feet times feet, which is equal to pounds per square feet, which is exactly the units of stress that we want. So although it's not as clear as that cross-sectional area like with steel or with concrete, where we can calculate that cross-sectional area that the force is being applied to, the stress that is applied from soil is still in units of pounds per square foot, or any type of stress like that, kPa, like kilonewtons per cubic or per square meter, something like that. Okay, so let's show another example then. So that was a dry case. Let's say now we have saturated soil conditions. So now we have a groundwater table all the way at the top. If we were to still look at that little circle, we would now have it filled with water as well, right? So not only do we have the WS here, but now we also have WW. There's weight of water in here. So if we're looking at just the water only, the weight of water or the pressure due to water is shown by this, and it's the density of water that we know is 62.4 pounds per cubic foot times the height of the water. So if we were to remove all the soil out, this is what we call our U, or pore water pressure, and this is called our neutral pressure. And this is the same as thinking about like if you swim at the bottom of a swimming pool and you feel pressure on your ears. Like that's what you're feeling. You're feeling the pore water pressure. So the deeper you go in a substance, the more weight that substance is above your head, and you can feel that in your ears. Same thing that's happening here. So that's the pore water pressure. That's just the water within the pore space. Again, this only works if it is fully saturated. If we look for this table here. So if there's water above that, then we don't count, or if that the groundwater table is not to the top, then we do not care about the pore water pressure in this specific example. So what we see is the total stress, again, is a combination of both things right here. So the total stress is everything that has mass. So it could be water and solid. What we see is as the total stress increases, we should see that the pore water increases, or vice versa. So as the pore water pressure increases, then we would increase our total stress. This is kind of like the big picture of why of the stress distribution and in situ stresses. So we have total stress so far, which is our sigma shown here. And this is the weight or the density and the density of the soil, whatever state it is. So it could be saturated, it could be dry, it could be moist, it could be any of these states, but whatever that is in that circle, multiplied by the depth or the height above that is equal to our total stress. If we only care about the water, that's our pore water pressure. And this is shown by just looking at the density of water. So same equation, we're just looking at a different density here. So density of water, or unit weight of water, or the unit weight of the soil. So why is this important for geotech? For the most part, soil is getting its strength from friction. So we call soil frictional. So that means that soil fails through a process called shearing, and it's different than what we learn in like structural analysis, like shearing of concrete or something. It's a little different. Basically, what we think of this is like these particles, these little tiny soil grains rolling over each other and sliding along a certain slip plane. So as that normal force increases, what we see, so as normal force, so we could say this is as a sigma, what we'll see is the frictional resistance also increases. And this probably makes sense. Like a lot of you guys could probably picture this if you like take sandpaper or something, for example. Sandpaper has friction on it, right? So if we had a block with sandpaper here and we put it on a table and you attached a string to it like this and you pulled it, it's relatively easy to pull, right? But if we added a bunch of weight on top of it and we increased the normal force applied, then it gets harder to pull, right? Because it increases the friction. If you remember from your physics class, the friction force or friction resistance is a mu, so a friction coefficient times the normal force. So if we increase that normal force, then we increase the resistance due to friction. And we see the same thing in soil. So since soil fails in friction, if we have an increase in situ stress, then generally that increases the strength of our soil. So as stress increases, soil strength increases. So this also, though, results in a higher load from our soil, which could be problematic, especially if we're making like tunnels or something. So think of it that way, like we want the soil to be as dense as possible, to have a higher unit weight, so it has a higher strength, but then it's also applying a larger load. So if we densify this entire like soil area and it's really, really high strength, and then 10 years later, we want to install a tunnel underneath that, now we have a heavier mass of soil that is being applied to that tunnel. So it's not always beneficial to make it as strong as possible in that case. All right, so for in situ stresses, if we are assuming homogeneous, and let's just look at this example here where we have water saturated. What that means is we could draw the, what's going on? We could draw the profile of our total stress. So in this case, our total stress is going to equal what type of density? Who could guess? Saturated, yeah. So this would be our gamma sat, because if we were to look at a little circle and zoom in, we would see soil particles, and then we would also see a bunch of water in here too, right? So we would see two things in our circle, and our total stress is the whole thing. So this would be our gamma saturated. If we care about point A, then we see H, like we just multiply it by H because that's everything that's on top of it. So if we were to actually draw this profile, what we'd see is if gamma saturated stays the same, this is just a function of H, right? So at H is equal to 0, so right here at this point, we would have a stress equal to 0. At 1 times 2 times 3, as we go down in depth, what we would see is it is a linear relationship, right? So this is really nice. So in homogeneous soil, to draw the profile of our total stress, it is just a straight line with depth. Unless the density changes or something else changes, then that line might deviate and have a different slope. So the pore water pressure or the neutral pressure, we could also draw this profile, right? This is shown by U. So U is our pore water pressure. So it's the same. I mean, like think of it like U just being for water and sigma for soil. I don't know if that helps at all, but for that U, it's the same thing basically. So if we were to draw a profile, we could measure at H, and this, since the unit weight of water is staying the same, then this is just a straight line the entire time. So what would happen if we lowered the groundwater table like that? So now instead of our sand not being saturated, we would have this as a moist unit weight, right? So now this would be, our total stress would not be saturated, it would be M. And if we were to look at this, we would still have the same amount of soil particles, but now we would have less water. So we might have a little bit of water, but it won't be saturated. So our total stress would change a little bit, but not by too much, like because the water, there's a majority of soil particles compared to water. So our total stress would change. But what would happen to our pore water pressure at this point? Our pore water pressure will decrease, or pretty much go to zero if it's above A, right? Because there's no standing water above that point anymore. So that means that would decrease our total stress as well, because what we're doing is we're losing the weight of water in this. So if we know that the strength of the soil is a function of our stress, if we are estimating the strength of our soil from our total stress, and let's just say we go into a drought scenario or something, and the groundwater table lowers like randomly like 1 year, then we are potentially losing all of our strength, right? Because the water table is going down. We designed a certain structure to have a strength, or the soil to have certain strength from this value, this total stress value. But in drought scenarios, we lose all that strength, and then we could potentially have failures and stuff. So this is all to say that the pore water pressure is based on nature, right? Pore water pressure is water, and the soil, it could change throughout the time. So what we do is we don't trust this when we actually do our strength calculation. So we've developed a very easy equation called the effective stress, which is shown by this little prime here. And all we do is just subtract out the pore water pressure. So if we take the total stress, and then we say we don't trust the water pressure because it could change through the seasons and over time. If we take that out, then what we design our strength for is our effective stress. And it's just this equation here. So very, very simple equation, but super important, because if you are using total stress to estimate the strength and you accidentally do total stress for your calculation instead of effective stress, then you could be designing something that could fail in a drought scenario or something like that. So effective stress is super important. It's one of the most important questions or equations in geotech, and it's one of the easiest. So that's why everyone should like geotech. So pore water can't be trusted. So let's talk more about the effective stress. So the effective stress is our total stress. So sigma without the prime on it, which is just the weight of everything above that certain point. So just think of dog piles, like whatever this point, and you have X amount of things above you, you feel that weight. And then we subtract the pore water pressure. And the pore water pressure is just the weight of the water only. So we're only looking at the water at that point. That's equal to the effective stress. So what does this physically represent? So for granule material, so sand or gravel, what this actually represents is that intergranule stress, which is kind of cool. So this is actually like looking again, when we zoomed in at this circle of grains, what this stress is actually representing is the points of contact between everything. And that's what we want to design against, right? Because like this is the thing that's actually holding our strength or our structures together. This is the points of contact that is keeping the soil from moving away when seepage force is there, or when we load it with a structure or something like that. And there's a lot of work that's actually gone in to look through this. And we see how the pore water pressure within this adds to this benefit, which is why we take that point away. So we don't design, because this groundwater table, this pore water pressure can change. So we don't want to design our strength with this. So this is just going into the math a little bit. There's a lot of work in your textbooks that show how this is actually derived using free body diagrams, and the force divided by the points of contact, A, and then eventually in granule material, we assume that these points of contact are super, super small. So eventually we get the derivation of our total stress equation here. And then we just switch this around to solve for our effective stress is equal to our total stress minus our pore water pressure. So just showing that this actually like makes sense when we zoom in and look at the free body diagram of the actual granule structures. So this is it for granule material, and it kind of makes sense. You might be asking then, okay, well, what about fine grained soil? So for fine grained soil, clay. If you remember when we talked about this, the clay particles don't actually ever physically touch. You know, they look like little accordions together, and there's all these small interactions of forces that actually have these things suspended. And that's how we get our cohesion. That's how we get the plasticity and all those fun things. But for this, then how is force actually transferred through everything if the mineral structure doesn't physically contact? And the question is, they don't actually know. So there's actually been a lot of empirical studies that back in the 60s that have determined that this effective stress relationship still checks out, even though there's no physical like phenomenon where we can actually track the statics through everything. So this is a big area of research. Effective stress parameters in clays are still used, but they're almost over conservative. So I mean, if you're interested in like the material science side of things, this is a big area that is currently still being researched, because it was only until the 60s that they determined that it checks out. But there's a lot of verification still in this realm. So what we know is this effective stress parameter is what good for all types of soil. And that's what we're going to assume here. For sands and for clays, we will always use the effective stress instead of the total stress. So it's important to calculate it. So let's look at an example of calculating the in situ stresses. So when we say in situ stresses, generally what we will always talk about is our total stress, our pore water pressure, and then our effective stress. So these are like, if you think of in situ stresses, these are the things that we care about. It's easy to calculate the total stress. It's easy to calculate the pore water pressure. And then we want to calculate the effective stress from that. So let's calculate the total stress, the pore water pressure, and the effective stress at elevation A. So this is just a weird way of showing like just a cross section of soil. So what you could picture this is like something that extends beyond here. You have this soil here that's 5 meters deep at point A. And this soil has a density, a saturated density of 2 or whatever. So our total stress is everything that has weight above it. So the delta or the gamma times H in this case is 5 meters because we want to check it at point A right here. So if you were a sand particle at point A, the total, everything that you would feel above you is the density of that soil, right? Not the air, just the density. So since we're given this in megagrams per cubic meter, remember that the density, the gamma, is the density times the gravity, just to get it in the correct units, times H. So if we did 2.0 megagrams per cubic meter times 9.81 meters per second squared times 5, what this would give us is 98.1 megagrams per second squared times meter. And luckily, if we do all this out, 1 Newton is equal to this, blah, 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 you get this here. So most of the time, that's why we show density in terms of unit weight instead of density, I should say. And this doesn't work. Anyway, so this is why unit weight is better. And this is why most of the time you will always be given the unit weight, because it's easier to transform that into stress, into force parameters. Okay, so knowing all these, so this means that the stress at point A, the total stress, you would be feeling 98.1 kilopascals above you. That's what that is saying right at point A. So for the pore water pressure, this is the height of water above you times the density of water above you. So remember, this is when you're looking for the pore water pressure, what you do is look for the triangle. Where's the triangle here? At point A, right? So how much pore water pressure, what's the height of water above you if you are sitting at point A? 0, yeah. So for this, our pore water pressure would be 0 because there is no standing water above you. So although there is still water in the soil, like because it's still saturated, that's included in our total stress. That's included in this value right here because this since we're looking at the saturated density, that means this already is included with the water here. Water is already included in that. So there's no standing water, so we don't include that in our pore water pressure. So for this, our pore water pressure at point A is 0. So what would be our effective stress? Be the same as our total stress, right? Because we'd just be subtracting 0 from that. So effective stress is always calculated. This is our sigma, so our total stress minus our pore water pressure. And we see that is equal to our effective stress or our total stress. So in cases like this, where there is no standing water above you, our total stress is always equal to our effective stress, which is kind of nice. It's only when we have standing water or like a water table above you with a pore water pressure do we have a difference between effective stress and total stress. So let's look at a different example then. This time we have the water table all the way up here. So now we have standing water up here. So our total stress is going to be from everything that has weight above us, right? So if we're hanging out right here at point A, our total stress is going to be from the soil. But if you were like sitting and trying to hold up at point A, what else would you have above you? You would have the weight of the soil as well as what? Yeah, you'd have those 2 meters of water that you have to hold up too on your plate. So we also have to add this extra amount. And this is where the total stress comes in because you'll see in the future, like any structural loading is included in this total stress. Any like potential of like a structure being on top in the future, that's included in this total stress. So for this though, the density of water being 9.81 kilonewtons per cubic meter times 2 meters. And then we see this all checks out here. This means now our total stress is 117.7 kPa. So our pore water pressure, this is only the weight of the standing water above us. So if we were to remove all this soil, let's just say we remove all the soil, how much water would be above us? Who thinks 2 meters? Who thinks 7 meters? Who thinks 0 meters? Who thinks they want to go to sleep? If there is going to be, if we remove all this soil, like all this soil right here, how much water would be above us at point A? What would be the height of water above us?
Are we assuming that taking out the soil doesn't drop the water table?
Right, yeah. Yeah, for 7. So the pore water pressure at this point is going to be 7 feet of water because that's. So again, we have to think back to like the Bernoulli stuff. So our HW is going to be right here. This is the height of the water at point A. And that's 7 meters, so 9.81, which is the density, times 7 meters. Our pore water pressure is 68.7 kilopascals. So our effective stress is just our total stress minus that pore water pressure. And what we see in this case is it is 49 kilopascals. So we actually change our effective stress in this case, which is why we would need to design against our effective stress. We are lowering the amount of like stress that's being applied. So if we compare these two, the one on the right, we see that we have these values here, 117 minus 68. And then the one on the left, we see these, which means in this case, like we could see how just the increase of groundwater table is going to change our effective stress. So although it increased our total stress, which might give us an idea that there is more strength, since we have that extra water at the top, we actually see a decrease in effective stress. So that's why we always have to design for effective stress. So this is from example 6.6. You can go through that in a little bit more detail. What's important too is that these are all hydrostatic. So these are just snapshots of where the groundwater table is staying where it is. But over time, we know that there could be a change of groundwater table where the groundwater table will actually rise or the groundwater table will actually fall. And that induces different pore water pressures, which we'll talk about here in a little bit. All right, so let's look at another example. For this looks more like just a standard like cross section of soil. We see a groundwater table right here at 200 or 2 feet down in depth. So this is our ground surface. We see a sand layer with that density, a sand layer with a saturated density, and then a clay layer underneath that of 4 feet in depth. So let's look at this example real quick. So remember, we always first need to identify where the groundwater table is. So ideally, like if you need to color it blue or whatever, just know that the water is only going up to that point. So the saturated density has the weight of the solid plus the weight of water in it. So if we were zooming in and looking at that, then we're looking at that weight here, this WT. That's everything that is in this mass. So first, what we can do is find the total stress at point A. So total stress, that is our sigma, our pore water pressure, that is our U, and our effective stress, that is our sigma prime. So total stress at point A. So this is everything that has mass over it. So we have first, starting from the bottom, I think it's always easier to start from the bottom. We have 4 feet of something that weighs 95 pounds times the per cubic foot. And then above that, we have 2 feet of something that weighs 112 pounds per cubic foot. And then above that, we have 2 feet of something that weighs 105 pounds per cubic foot. So what we would do is add all of these sections together, and our total stress would be 814 pounds per square foot. So if you were hanging out down here at point A, you would have this much pressure. You would have to hold up this much pressure at this point. All right, so the pore water pressure, we're still looking at A here at that point A. So now we care about the weight of water above us. So U is the weight of the water overhead. So the density of water, we're assuming 62.4 pounds per cubic foot. The weight of water above us, we have 6 feet, right? Because we don't care about the soil layers. We're just looking at the water. So this is 6 feet. So this would mean that our pore water pressure at point A is 374.4 pounds per square foot. So our effective stress at point A, we just subtract these things because we can't trust that water, and we get 439.6 pounds per square foot. So this is again a hydrostatic condition. So what would happen if we had a change of groundwater table? So for that, we wouldn't have hydrostatic anymore. Let's just say that this weight of water overhead now means something a little bit different. So let's say like at point A, right here, like we have a downward gradient. So we have a different, remember when we were talking about permeability, we have a change of head from one side of the soil to the other, right? So when we have a change of head from one side of the soil to the other, we have flow from that higher head to a lower head. So let's say for right here, we have this downward flow, which would mean the water table, the pressure head at point A is lower, right? So if we care about the pore water pressure at point A, now we would have a lower value. We'd have this HW being a smaller value than its original value of 6 feet. So this pore water pressure would change, and now we're going to lower this, right? So UA will lower because now instead of 6 feet, we would have whatever this is, like we just say like 3 feet or something. So we're multiplying that head by something different. So if our pore water pressure lowers due to downward seepage, how will that change our effective stress? Yeah, we are subtracting something by a smaller number now, right? So this number will go down and we will actually see an increase in effective stress. And think about this from like the granule level. Like this would make sense because this effective stress is the connection point between these soil particles. So if we have water flowing vertically and pushing on these soil particles, then there's going to be more contact between them, right? Because downward seepage, the water molecules are hitting the soil particles and it's squeezing them together a little bit more. So it would make sense that our sigma effective stress will increase. So let's think about the other way around now. So what would happen if at point A, we have a higher head than point B? So this would mean that the water at point A is going to want to flow up, right? So now at point A, we have a higher HW than point B. So this would mean that our UA will now increase, right? And how would that affect our points of contact? Now we have soil particles going against gravity, or water molecules going against gravity and pushing our soil particles up. So this will decrease the connection stress between our soil particles. And so this will decrease our overall thing. So there's a certain condition. What would happen if this value, our sigma stress, goes to 0, right? And we'll talk about that. And this meme is super outdated now, but that's like, if this stress goes to 0, if these interlocking particles goes to 0, what do you think might happen? Yeah. So we would have no interlocking stress. And this is actually what quicksand is in the movies. So quicksand is just sand that looks like you could load weight on it, but the movement of water coming up through it actually makes it so it just acts like water. So you don't sink into it, you just float in sand because it just looks like there is water in it or not. But it looks like it's hard sand, but it's actually not. Okay, so let's look at more examples of hydrostatics. So groundwater table is at the surface. So let's just say we move all the way up here. Now we have a saturated value. So let's just say it's equal to this. So total stress at point A, we add everything up above us. We have 4 feet here of 95. We have 2 feet of 112. And now we have 2 feet of 110 since this is saturated conditions. So our total stress is the combination of all of that. It's 824 pounds per square foot now. Our pore water pressure at A, if we were to stick a straw down here and measure the height of water, we would see that we have 8 feet of water that flows up to the top. So 8 feet of head. And so 62.4. So this means our pore water pressure is 499. So our effective stress, we just subtract these two and we see 325 pounds per square foot. So we see that our effective stress is decreasing because we're still increasing our water. So this is from before when our groundwater table was at 2 feet below the surface. Let's say now like our groundwater table's at the surface and more floods come and I don't know, like it just starts raining a lot. And we see that it actually now we have standing water above our soil here. So we have like lake conditions. So this is now, let's just say we have 3 feet of this and we have little fishies swimming around. So this is all just standing water. So we still have saturated conditions all the way through. Our total stress, or what we show is that this is a material that is 62.4 pounds per cubic foot because that's the weight of the water. So our total stress, now we include this still. We include this layer. We include this layer. But now we also need to include the weight of the water above us. Since this weight of water is still pushing down at the ground surface. So this is something that still needs to be held up at point A. So now what we see is our total stress is increased drastically at 1,000. And the pore water pressure at this point is higher too, so it increases as well. So now we have 11 feet of water, and this is at 686 then. So our effective stress is actually the same. So we still see, we subtract the total stress minus the pore water pressure, and our effective stress value is staying the same compared to when it was at the groundwater surface. So as flooding comes and as we increase the groundwater table above our surface, so we get standing ponding water, we actually see that the effective stress at a point below the surface doesn't change. So there's some trends here that we can recognize, in situ stresses and the groundwater table. And these are all in hydrostatic conditions. Let's say as the groundwater table increases, so as the seasonal, groundwater table rises, what we would see is the effective stress decreases. And think about the equation, like what is actually happening here. So with this equation, what we're doing, we're actually changing, we're not really changing the sigma too much. So I'm just going to say the change of this total stress doesn't change as that much because the majority of the soil is weight of solid. But what we're doing is we're increasing the pore water pressure. So if we increase the pore water pressure, then we are subtracting a higher number from our total stress, which causes a decrease in this value. So, but as the groundwater table increases above the ground surface, the effective stress stays the same. So looking at our equation again, for this, we would still increase this HP times gamma, but we would actually add the same exact thing to our total stress, since this is an additional thing we have to hold up at point A or at whatever point we care about. So as the groundwater table is increasing through the soil, the effective stress is decreasing. But then as soon as we get above the ground surface, it stays the same. The effective stress stays the same. So the increase in the pore water pressure is equal to the increase in total stress. So our effective stress actually doesn't change. So as the groundwater table decreases, adversely to the first point, we would see the effective stress increases. And again, think of this as the intergranule stress. So as that stress increases, as our effective stress increases, we see that the soil strength will increase, which is generally good. But also the resulting load from the soil increases, which means the pressure on the soil increases. So think of it this way though. So if we have a soil structure that looks like this, and we increase the effective stress so much, we just keep increasing it, what we could actually see is compression of our soil. And I didn't include that slide, but for next class, we'll go over this. This can actually cause settlement just by lowering the groundwater table. So I'll share next class. I don't know why I didn't include it on here, but actually in California, it's a really interesting scenario over the past 70 years on the east side of California, where they have been lowering the groundwater table so much due to overpumping for the crops out there in the San Joaquin Valley, I think. The groundwater or the ground surface is actually settled more than 30 feet or something. There's a pole out there that you can see the sand layer from 1960 and how much it's lowered. And that's only because they're lowering the groundwater table, which is increasing the effective stress, which is actually causing these soil grains to squeeze together so much. So they're not removing soil at all. They're just pumping the groundwater table out and it's settling that much. So it's a really interesting case history. So although the increase in effective stress is generally good because we have more strength, it could also be bad because then we could have settlement or we could have compression of the soil grains if it's too much. All right, so I know this is a lot. We'll kind of recap this next class and show a few examples. And then I'll have a homework posted next week too. So no quiz, no lab today. what I just went over doesn't make any sense at all, then let me know and we can explain it in further detail later on. But have a good weekend and I'll see y'all next week.